Yeah, in this video, I'll show you how to actually compute a line integral through a vector field. So remember, we integrate a vector field along a path C. That's like our region of integration or our interval of integration. And we saw previously with this Riemann-Sum-like idea that we can break up our line C, our path C. So we'll do that here. But if we parameterize the path, that is, if we can write it as r of t for some time parameter t, then really we could think of this as a subdivision of time. That is, each point will correspond to some time interval, or some point in time. We can talk about the difference between these points, as we did with the Riemann sum. But we'll add something new here. So at each point, I'll also draw a tangent vector. That is, this is the derivative of r prime at that point. And I'll scale it by the change in time, that is, by our time slice. And an idea here, and this is really just the idea of local linearization or local approximation, is that as our slices of the curve get small, our displacement vectors delta r will be very, very close to our derivative vectors r prime scaled by delta t. So we'll use that fact that, remember, this dot product is what we use to think about work, or whether a vector field was helping or hindering us as we move along a curve. And this really was the thing that we added up for our Riemann sum. This dot product, we can approximate it by, well, evaluating the function. We don't need to just call it Ri. We can say R evaluated at the ith time interval, or time point. And we'll dot that with its approximation, the derivative of R at that point in time, times delta t, the change in time. And if we take the limit, that is, let our time interval get close to 0, everything will shrink and get close together. We'll add them all up, and we'll get a form of an integral that we can use. So this path integral, we'll write it as an integral from a to b. A and b were the bounds of our parameterization of the vector field f defined at r of t, dotted with r prime of t, the derivative, dt. And this looks a little complicated, but the first piece, that's a vector. The second piece, that's a vector. We're dotting two vectors, which gives us a scalar. So this is a scalar function of t. And when we're done, this should look like a Calc 2 integral. It's a single variable integral. Let's see some examples that will make it more clear. So in this, we will integrate the vector field f, which is 0x. You can see I've drawn this path C1 that goes from the point 1, 0 up to a 0, 1. Maybe just to make sure we're all on the same page, do you think this integral will be positive, negative, or 0? Maybe pause the video, take a second to think about it. And hopefully you'll agree that the line integral here should be positive. That is, the vector field, it's not pointing exactly in the direction of the path, but it certainly would be helping us as we move along that path. But we can do better than that. Let's compute it. So the first thing to do is to parameterize that path. This is a line segment. Hopefully this is not too bad. We need to compute the direction vector. That is, we can take the endpoint, 0, 1, we can subtract from that the beginning point, 1, 0, to get a displacement minus 1, 1. And we can stick that in the parametric equation for a line where our bounds for the parameterization are 0 and 1 for t. So putting that all together, this path integral will go from t equals 0 to 1. We need f where we're plugging in that parameterization. So we'll plug in 1 minus t for x and t for y. We'll dot that with r prime of t. We'll find that in a second. dt. Now what is f of 1 minus t? Remember, f takes an input xy and it spits out a vector 0x. So the first component will be 0 and the second component will be whatever the x component was. So that's 0, 1 minus t. We'll dot that with the vector that's the derivative of r of t. That's minus 1, 1. And we can take that dot product and we see we get just 1 minus t. And that's an easy integral to take. I'll let you check this is true. Let's try one more. So this is the same vector field. F of xy is 0x. But this time I want to get from that same starting point to the same ending point, but taking a different path, taking a quarter circle path instead of a straight line. We'll parameterize that quarter circle using cosine t sine t, the parameterization of a unit circle, with the t bounds from 0 to pi over 2. It's just a quarter circle. We know we'll need it later, so we'll write down r prime, the derivative. And plugging that in, we need our vector field f evaluated at cosine t sine t. We'll dot that with the derivative function, minus sine t cosine t. That's the derivative of the parameterization. And well, the vector field evaluated at along this parameterization should give us 0 cosine t. Take the dot product to get cosine squared t. You learned 3 different ways to do this integral in your Calc 2 class. However you do it, you'll find that the answer is pi over 4. So still positive because the vector field is still helping us as we move along that curve. And actually, pi over 4 is a little bigger than 1/2. It's what, 0.7 something. So moving along this curved path, this quarter circle path, we would get more help from the vector field. So we'll continue this discussion in class. See you soon.